Hello everyone, this is Feng Huang from the Hong Kong Polytechnic University. Today we are sharing our work about using LiDAR to help detect the potential cyclists for GNSS RTK in urban areas. So before I start, I will show you some RTK performance under the commercial GNSS receiver. So in the left-hand side, you can see centimeter level accuracy can be obtained in the open sky if the integer ambiguities are fixed correctly. However, in the urban areas, the large error will occur due to the unreliable integer ambiguity resolution. So one of the key changes for this one is the cycle splits, because the RTK relies on the carrier phase and the integer ambiguity resolution. So in the open sky, the double difference carrier phase are very smoothly. However, if the vehicle enter the urban areas, so a lot of signal reflection will cause the unexpected changing in the integer ambiguity. So also miss this one, you can see a phase change in the double difference carrier phase. So the cycle split will cause the inconsistencies in the integer ambiguity. Therefore, there is very important to identify the inconsistencies, which also means the cycle split in the GNSS RTK to improve the urban RTK performance. Therefore, the researcher proposed several methods to identify the cycle splits. Essentially, the principle are similar. They try to use additional information or additional sensors to detect the inconsistencies in the integer ambiguity. For example, the also open source, the RTK Leap, they use the LI and the phase jump to monitor the potential cycle split. Another researcher team from the Canada, they use the inertial sensor to detect and correct the cycle splits in the carrier phase. In 2018, the team from the Wuhan University, they proposed to use a tightly coupled multi-GNSS and low-cost IMU to eliminate the errors raised by the cycle split. In 2020, the researcher from the Chinese Academy of Science, they proposed to use Doppler integration to detect the cycle split. In the same years, another team from Japan, they proposed to detect the unlost measurement to reject the potential cycle split caused by the signal processing. So for the LI indicator, the LI indicator determined by the receiver checking loops, so has already presented in the RNS file. So you can have several numbers to identify the cycle split. You can see the 0 here. Example, it means the no cycle split or unknowing. However, in the urban area, you can see a lot of the cycle split which marked in red in the typical urban areas of Hong Kong. So for example, you can see a cell line, it means a C34 corresponding to here. You can see a cycle split marked in 3 here. Another researcher, they use the IMU to detect the consistencies in the carrier phase. However, the IMU sensor relies on the correction of the internal bias, which means we need additional sensors to correct the bias of the IMU. Another research team, they use the consistency check based on the Doppler measurement. First, they compute the between epoch carrier phase. Also, we compute the between epoch, the range difference based on the Doppler integration. And last, the residual between these two can be used to identify the potential cycle split. As shown in the figures, so most of the residual, they are near to the 0, which also LI also can be detected. But some large errors here you can use to detect the cycle splits, which is not marked by the LI. However, the Doppler can be affected by the multipath in the urban areas. So recently, the LiDAR is typically used for the autonomous driving. So and LiDAR autonomy can provide very accuracy-related pose estimation. Inspired by this key feature, the paper proposed to use LiDAR to detect the cycle split. So the idea is first we have the LiDAR scan matching pose. We will transfer it to the ECF domain. After that, we can have the double difference measurement from the GNSS receiver. We can also have the LiDAR predicted the double difference measurement So we will combine these two. We have a triple difference cycle state detection. We will resolve the integer ambiguity resolution using RTK leap after detect the potential cycle state. In terms of the LiDAR odometry, we use very popular the long method, which extract the edge and the panel features to do the scan matching. For more details, you can refer to this word here. We also can show you some demos of in Hong Kong urban areas. You can see the post estimation. It can be achieved by the ROM. So for the GNSS RTK, you can see we have the satellites and we also have the receiver here. So the first is the short range and the carrier phase measurement model. We have the range distance and also the clock bias and some others error here. So using the single difference, we can remove the atmospheres and the cross related errors with the sensor lights here. So for the double difference, if you include one more the master satellite, we can remove all the systematic errors. After that, the flow solution can be resolved using the waiting list square. So after that, we have the flow solution. We can further fit into the fixed ambiguity resolution. So the problem is that how can we detect the potential the cycle slips in the current double difference ambiguity resolution? We will introduce the triple difference method. So first we record the double difference carrier phase measurement here. Then the triple difference is using the current epoch and minus the previous epoch. So first one we have the triple difference, the range, also the changing of the double difference ambiguity, also the unmodeled errors, which is approximated to 0. Luckily, we can use the LiDAR odometry to provide the relative mode estimation for the eliminate the first turn. So for the details, we transfer the LiDAR scan matching to the EMU frame and also the ECES frame. After that, we also record the triple difference based on the LiDAR pulse and the base station. Here you have the triple difference, the range distance approximately. After that, the difference between the triple difference, the carrier phase, and also triple difference range should be nearly to 0 if no cycle slip occurs. So we can detect a cycle slip if it is over a threshold. We use 3 cycles in here. So the cycle slip detection, we finally will feed into the initial resolution to re-estimate the ambiguity before resolving the RTK solution. So for the experimental setup, we have a U-Bros F9P, which mount on the rear of the car. We have a LiDAR sensor on top of the vehicles. We also have the sensitivity to provide the ground truth. So the processing settings for the RTK leaf are shown here. We use GPS and Beidou L1. So we select the typical urban areas in Hong Kong, which contains numbers, trees and buildings, which is easier to occur the cycle slip. So first one, we need to labeling the ground truth. So we have a triple difference carrier phase, so also have a triple difference range by the ground truth. So we can monitor the consistencies between these 2 epochs to determine if I have a cycle slip. The second one is the cycle slip detection rate. We detected by the LiDAR-aided method. So to also maybe the LI which contains into the ground truth labeled, divided by the total number of cycle slip ground truth labeled. So let's show some result first. So you can see the LAD method, which means the LiDAR-aided cycle slip detection we proposed. Can detect most of the cycle slips compared to the ground truth labeled. And you can see the LI indicator, it cannot detect the small cycle in the areas. For example, on the right hand side here, also here. However, you can see the LI indicator. It can detect more cycle speed than the ground truth labeled here. So the possible reason for this one is large numbers of cycle speed marked by the LI in the beginning or the end of the measurement, or some is continuously the epoch, which ground truth cannot mark because ground truth use the continuous the measurement. As these two methods, they are using different strategies to detect the cycle state. We are thinking that the LiDAR-aided method could be complementary to the LI method. To verify this, we are further evaluating the positioning result with the cycle state detection. So for the method we evaluated, we use the RTK leaf. RTK leaf, for the setting of RTK leaf, we use the fix and hold with the forward mode, which means that the current filter solution will be used to constrain the state estimation in the coming epoch. The second one we use the comparison is that we only use the LiDAR-aided cycle state method. After that, we will combine these two, the LiDAR-aided cycle state and the LI map in the third and the fourth methods. But differently, the third we exclude all the unhealthy cell line. We detect it with the cycle state, and the proposed method we will re-estimate both the mark by the cycle state. You can see the results in terms of the positioning. The RTK LAR proposed by ourselves, but by us, they rank the best among 4 methods. You can see the better methods, better performance in the areas marked by the purple and the also oranging areas, which also occurred easily. The RTK-LA, they are worse only because it only use the LiDAR-aided methods. Then the RTK-LAE, they also have a better performance as it excludes some cell life with the cell state, but he has a lower availability as it may break the geometry in some epochs. In general, the LiDAR-aided and the LI indicator for the cell state is complementary according to our experimental result here. However, there are still some large error in the beginning of the evaluation for all the methods. So due to the excessive the signal reflection from the buildings and also the trees. So here comes to our conclusion. First, we proposed the LiDAR-aided GNSS cell state detection. The second, we found that the LI, which determined by the receiver tracking loop, the method and the LiDAR-aided method, they are complementary for the cell state detection. We also improved the positioning accuracy and the facing rate in the urban areas. One of the future work is that we are working on the GNSS multi-frequency support, as we show the result of the L1 frequency. The second, we will evaluate the performance in the the urban areas. We also open source our UrbanNet dataset in last years. It contains the multi-GNSS, also the LiDARs and the camera measurements in the urban areas. You can check it out if you are interested. Okay, this is the end of our presentation. Thank you for your attendance.